is over. Here we go. There are only 3 topics: parametric equations, vector valued functions, polar coordinates, and how they relate to calculus. I'm able to get these done in 7 sections. So I'm going to give you 7 little lessons on each of those topics. Now, the first 2 lessons will be on parametrics. The one today is really going over what it is and how you use it. There's not a lot of calculus today. Tomorrow, how does this relate to calculus? Now, you may have done parametrics before, I'm not sure, so you might already know this, but it's a little quick overview. Now, I told you something else in the email I sent to you yesterday. I told you that I was going to send you a list of questions that I wanted you to finish for a grade. Well, I've amended that a little bit. Instead of sending you one big packet of questions, I am just sending you the questions 3 at a time. My plan is to have approximately 3 questions per lesson that I will assess you on. There'll be 21 total questions. But I thought if I gave them to you 3 at a time instead of a packet of 21, it might be a little bit easier. What I'd like you to do is to do these problems. And I would like you to hold off on them and not send them all in to me, small 3 at a time. But when you're all finished with all 21, send them all to me and I'll grade them. You don't have to wait and do them all at the same time. You can do them as you go. Just send them to me when you're all done. And I will give you a list of all the numbers so that you know what you'll have to do. But on this paper, I will always have what those problems will be. So for each lesson, you'll be getting from me this sheet, which should look very familiar because that's what I would give you if we were in class. Then I'm going to do the notes, and then obviously I'm making this video. So you get 3 things that will be listed in Edmodo: a blank set of notes, a completed set of notes, and the video explaining them. And watch the video, look at the notes, and just make sure you know how to do the stuff. All right, here we go. A reminder of parametric equations. Okay. We are basically introducing a third variable into a function. For example, you've got a graph. Let's say the graph looks like that. Graph looks great. Just a parabola. But what a parameter will do is tell you what direction something is traveling along this parabola. So we have little indicators of lines. So we want to add a variable of time. Now, it doesn't always have to be time, but that's the thing that we use the most. So we actually call this parameter, we usually call it t. So we're going to be creating a graph in terms of an x value and a y value as it relates to a third variable of t. T is your parameter, and as such, these are called parametric equations. Now, how do they work? Here we go. Got a parametric equation. The x value of my equation is represented by that formula, 2t plus 3. The y value is represented as t squared. Easiest way to do a parametric is to make a table. We're going to make a table of x and y values based on the variable t. Now we're going to have an interval of t from -2 to 3, so let's just start at -2. And we'll pick all these points, and we'll kind of see how this graph is taking shape. So if I put -2 in for x, I get -2 times 2 plus 3. -4 plus 3, so -1. And the y value is t squared, so it's 4. And just do that for your t value. 2 times -1 is -2. -1 squared, and we're going to go from there. This is 3. 0 squared is 0. And you can tell x is a linear function. It's always going up by 2. So that will be 5, 7, 9. T is a square function, so we're going to square that 1, square that 4, and square that 9. So what I've got is now x and y coordinates based upon a third variable. So let's graph that and see what it looks like. So if I graph -1, 4, 1, 2, 3, 4, graph 1, 1, graph 3, 0, graph 5, 1, and graph 7, 4, 5, 6, 7, 2, 3, 4, and 9, 9 way up here. So this shape, it may look like a parabola to you. Okay, didn't do so bad there. But it's not just a graph, it's also a position. I know here is where t is -2. I know here is where t is -1. I know here, I should have flattened out more, sorry, that t equals 0. T equals 3 up here. So this graph has a direction. It's going this way. Now I'm going to show you how to use Desmos.com website to graph a parametric equation. I'm going to graph this one. All right, as you can see, I'm on the Desmos.com website, and just want to show you this really fast. If you were to graph an actual coordinate point, the coordinate point would show up in your graph. Now we're not doing a point, we're doing a parametric equation, but a parametric equation is written as a point. There's an x value and a y value. The x value was 2t plus 3, and the y value was t squared. And you'll notice down here it asks us for our interval for our parameter. We went from -2 to 3. And you can see over here, here is our graph. That's only that part of it. Now, what I want to do is kind of an interesting thing. I'm going to do the same exact graph. I'm going to use the value of a at this time. Oops, let me fix that. Plus 3. Instead of the t, because I'm going to make the a slider. Now, I make it a slider. I click on one of these numbers down here, and I tell it what I want to start with. So I want to start with -2, and I want to go to 3, our same parameters. This time I'm going to animate it. And I'm going to start it here at -2 and watch what happens. So when it's going from -2 to 3, you see the direction it's taking. So I know it starts at -1, 4, and it goes off until 9, 9. So that is a parametric equation. It's not just direction, it's also a time. Alright, so how that worked? Looks pretty cool. You can also do the same thing on the TI-84 calculator. There's a parametric mode. I wish I had my emulator software with me to show you, but if you ever want to check it out, go to your mode, go down to the parametric. If you hit y equals, you're going to see x and y, and you're going to be using the variable of t. You're going to type it in, you can see the graph. It doesn't show you the direction, but it shows you the shape. So another way of doing it, to show you the shape, is to write it as a rectangular equation. Let's get rid of that parameter and write it like a regular old y equals whatever. And what we just do is we're basically just going to solve this for t and plug it in for that. So I know that x is 2t plus 3. I'm going to subtract 3 from both sides and divide by 2. So I know that t equals this. So I am just going to have to square that. I suppose you could leave it like that, but you know, my mathematical background and all the things I learned when I was in school makes me not want to leave it like that. Makes me want to put it into a standard form. I don't know why. It's like a habit. I don't know if it's even a good habit either. Let's see, 6 divided by 4 is 3 over 2. And so that's the equation that we see. Now, is that accurate? Is that correct? I don't know. I'm going to take it back to Desmos now, and let's take a look at it. So let's test that equation and see if it works. So what we have is y equals 1/4 x squared minus 3/2 x. Oh, it's looking good. What we got to do is we're going to move this up 9/4, and bingo. That graph is the same shape as the parametric graph, but it is not the same graph because the parametric is only taking into account a small interval of that, and parametrics do have a direction to consider. All right, you see how this equation matched the parameter, but it was the entire graph. Parameter is just part of it if you define the parameter. Now you don't have to define the parameter for something like this. So we have to see what the general sketch would look like. So again, we're going to pick a value for t, which is going to give us an x and a y value. Now it doesn't say what our t should equal, so let's just start at 0 and let's observe. So e to the 0 is 1. 3 times 0 is 0. E to the 0 is 1 plus 1 is 2. So we have 1 point there. It's 1, 2. It looks good. But then I notice this. If I try to put in 1, I'm going to get e and then e cubed plus 1. They're not exactly easy to graph, are they? So when we want to find our table, let's use something that makes the t, let's use a t that makes it a little bit easier to figure out. For example, what if I made it natural log of 2? And then what about natural log of 1? Or what is natural log of 1? 0. Okay. So if I put in natural log of 2, what is e to the natural log of 2? Well, it's 2. Oh, I can graph that point on the graph easily. That's much better. What would e to the 3 natural log of 2 equal? All right, well, remember your exponent rules. This is really going to be 3 to the natural log of 2 to the 3rd. And they kind of eliminate each other. You're left with 8. So this is going to be 8 plus 1, which is going to give us 9. Now that's jumping up real fast, so we know that's a general shape. So let's go the other direction. What if I went negative natural log of 2? All right, let's see. E to the negative natural log of 2. All right, exponent rules say I can bring that up, or log rules say that. So to the negative 1. All right, so these kind of cancel each other out. It's 2 to the negative 1, which is 1/2. So x is 1/2. In fact, if you notice, is there any value I can pick for t that will give me an answer of 0 or a negative number? And hopefully you can see it is not. T or x and y will never be less than 0. Will never equal 0 either. All right, let's figure out y. And I'm going to put it over here, but I'll have to erase it when we're done because it won't be in a good place. All right, that's what the y equals. If I let t equal negative natural log of 2. All right, some of you might see already what's happening with this answer. It's going to be negative 3. So it's going to take natural log 2 to the negative 3. 2 to the negative 3, he's kind of gone, is 1/8 plus 1, so we have 9/8. Not a fun one to graph, but I want you to be aware that x and y will never, ever, ever be less than or equal to 0 in this particular case. All right, now we have these values. So I get rid of this, and let's graph them. All right, so I have the point 1, 2. I have the point 2, 9. And I have this point 1/2 and 9/8, a little bit above 1. So really the question is, we know it's jumping up and going up here pretty fast. Whoops, missed it, sorry. But what about here? I said it would never get to 0. We'll get close, but we'll never get there, so it's an open circle. All right, let's check that on Desmos and let's confirm that answer. All right, looks good. Now again, it goes up forever. It's going this direction. Okay, just going up and up and up. So let's confirm our answer here. So let's again graph it at the coordinate point, e raised to the t power. And the y value would be e is to the 3t plus 1. And t is going, well, we had no values for t, so let's see what happens. So we just picked values just to see a general trend, and you can see the graph is going up as we expected it to. Now let's do our slider. Let's see what we got here. So we'll use value of a. You don't have to use a. It's just, it's the first letter, so why not? All right, let's add it, and let's see what happens when that slider follows. So here it comes. And notice how when a goes negative, it does not go past. Now, does it stop? Or does something interesting happen? Now what I'm going to zoom in right on this point here. Now we talked about this graph, that it could not possibly equal 0. So let's look what happens when this slider comes over this way. Now it's easier to see it when it's in motion, so let's put it in motion. You see how kind of like this takes off real quickly. Now watch when it comes back. So does it ever actually stop? I'm going to zoom in even more and more and more. And let's see what happens. I'm going to wait it all the way go out to 10. Now come on back. Here it comes. And so you can kind of see with this motion here, it actually never reaches the value of 0. But it gets closer and closer and closer to it. That's why the speed takes off. Coming this way, it really slows down, but it never gets there. Can you imagine that in reality? Something slowing down forever and never reaching a point. What a sad, sad existence. Such is the life of a graph. Now, what does our rectangular graph or a rectangular formula look like? Okay, so we have the same process. I'm going to solve this for t, so we're going to do a little natural log here. So when all's said and done, t equals a natural log of x. So I'm going to plug it in here and see what we get. So t is the natural log of x plus 1. All right. Exponent rules, log rules say that I can move this exponent up here. And I know that e and natural log are inverses of each other, so really they kind of are gone. X cubed plus 1. Oh, look at that. That would have been a little bit easier, wouldn't it? Instead of doing all the natural log of 3 to the natural log of 2 and all that, it's just x cubed plus 1. If I plug in 1, I get 2. If I plug in 2, I get 2 cubed is 8 and 1 is 9. But this is the entire graph of x cubed plus 1. So the parameter is only part of it. So we have to decide in this one, this is true, that this is the rectangular equation, but it's not completely accurate because it's too much of it. So we have to put a little restriction on it. If you know about the graph, what that restriction have to be is that x has to be greater than 0. That way, we just have this part, and it can't equal 0. Take a quick look at decimals and see if we got that part right. Let's see if our equation holds up. And you'll see that it surely does. However, again, even though that is a correct equation, that represents the curve of the parametric equation, it is not the parametric equation. The parametric equation is only from x is greater than 0. We're not doing bad, are we? All right, one more. So we're going to do the same thing. We're going to have an x. I'm sorry. We're going to have a theta value this time. Why theta? We're doing sine and cosine. Why not? All right, we also do not have parameter restrictions. So let's pick easy numbers. We're doing with trig. Let's do easy numbers. Here's 0. So the cosine of 0 is 1. The sine of 0 is 0. Right. Here's another nice easy one, pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. 1 times 3 is 3. Oh, this is nice. This is nice. Pi. Cosine of pi is negative 1. Sine of pi is 0. I like it when these work out nicely. 3 pi over 2. Right, cosine is 0. Sine is negative 1. And if I go to 2 pi, I'm just starting it all over again. So I don't need parameters on this because I can see it's a cycle. All right, now we're going to graph it. I think to make the graph a little bit nicer, let's just expand these and make all these ones. Okay, so we have 2, 0, 0, 3, negative 2, 0, 0, negative 3. Whoops, should have put it down there. Okay. Let's get rid of those. Let's fix that. There we go. Oh, it's in green, but it's okay. So what we have is we have our equation. Now, it's an oval. It's an ellipse. Now, it's going to be really hard for me to draw, so I'm going to try to fake it a little bit. I'm going to see if I can make this tool fake my ellipse for me. Here's the top half. It's not perfect. It's okay. And I'm going to duplicate it, spin it to get my bottom half. There we go. So that's a good fake right there. So there's my ellipse. Where does it start? It started at 2, 0. So it starts at 2, 0. This was theta equaled 0. And then it went up to 0, 3. So it's traveling this direction. All right, we're just going to throw this one in real fast and see if we come up with anything. Cosine, I'm just going to use t though because I don't know where the theta is on this. Now we are going all the way from 0, and we said 2 pi. So we'll just abbreviate it, or estimate it 6.28. So there is our graph. Our graph looks exactly the way we thought it would. Now let's see the spin. 3 sine of A. We'll add our slider, and we'll start it at 0. And we'll go, now it doesn't matter which way we go, or how far we go, because watch what happens. It's just going to spin around and around and around and around and around and around. But please note, it starts at 2, 0. And maybe I won't make it go so fast. If we probably go 10. Actually, all you need to do is go 2 pi. And it should be a little slower to see. That's a little nicer. What do you do with these? Well, I want you to remember something that you know. It's an identity that is true. Well, not what I was about to write. This identity is true. So we can use this. So I'm going to take this first thing right here and I'm going to divide by 2. That x over 2 equals cosine of theta. We'll do the same thing with that. We're going to divide by 3. So guess what I got? What's sine of theta? Y over 3. I take y over 3, and square it. Cosine is x over 2. I'm going to take x over 2 and square it, which equals 1. Now I've eliminated all the trig, and now I just have x's and y's. Now I don't know if it's been a while since you've done this, or if you have done this, but this is how you recognize the graph of an ellipse. An ellipse that hits the y axes at 3 and -3, and the x axes at 2 and -2. To put it in a standard form, though, I'm going to multiply by 36, the common denominator, and get this. All right, so last question. How do I take a regular old equation and turn it into a parametric equation? Well, it's actually pretty easy. You can just say, hey, let x equal t. So here's my first equation. Oops, well, that's my first equation, x equals t. And then if I let x equal t, well, then y has to equal 7t minus 12. Look, there's a parametric equation. Right? However, it does not satisfy this condition. If t equals 0, I get 0, -12. I need to get 1, -5. Darn it. Almost that easy, but I got to take into account this condition. All right, well, let me look at 1. I want my x value to be 1. Well, how do I make an x value 1? If t is going to equal 0, I just want to add 1 to it. So will this make this part true? And it will. When t equals 0, x is 1. So let me use that fact, that x is really t plus 1. Let's see what happens. And I think you're going to see here, that was almost a eureka, very well timed. You're going to see here that if I plug in 0, 0 times 7 minus 5 is -5, so the y value fits. So my parametric equation for this particular one is 7x minus 5. All right, quick intro on parametrics, so hopefully you're okay. Tomorrow we're going to have a lesson on some calculus. It was good talking to you again. I want you to take care, and I will see you tomorrow.